So, good afternoon, students. This is S. Arvind, Assistant Professor, Department of EEE, DBS at Kavali. So, in the previous sessions, I discussed about DC machines and transformer subject. So, under this subject, I am discussing the first unit of this subject, that is, sorry, second unit of this subject, that is DC generators. DC generators. So, in the previous classes, I taught you about introduction to DC generators, and next that is construction details of DC machine, and after that working principle of DC generator. And now I am going to discuss EMF equation of a DC generator. EMF equation of a DC generator. So here, so if you want to derive the EMF equation for a DC generator, firstly you have to consider some parameters. Those are, first one is phi. Phi, that is the flux per pole in Webers. Let phi be the flux per pole in Webers. And next one is P. Already you know that. Let P be the number of poles. And then let Z be the total number of conductors in the armature. Okay. Phi P Z. So here phi is the flux per pole. P is the number of poles. Z be the total number of conductors. So here the jet conductor, all the jet conductors are not connected in series. Okay, all the jet conductors are not connected in series. Okay, what is meant by this means all the jet conductors are not connected in series. They are divided into groups. They are divided into groups, not in a series. Now it is not connected in series. They are divided into groups, and from this one I am taking that A. So capital A. So let A be the number of parallel paths. Here I am taking A. There is a number of parallel paths into which these conductors are grouped. So I already said that all the jet conductors are not connected in series. So they are divided into groups. So by basing on this one, so basing on this one, I am taking A, that is the, let A be the number of parallel paths into which these conductors are grouped. So when the all the jet conductors are divided into groups, so depending upon those, I am taking that A, that is the number of parallel paths. Next, so each parallel path will have Z by A conductors in series. Here Z is the total number of conductors and A is the number of parallel paths. So first of all, we have, if you want to derive the EMF equation for a DC generator, we have to consider some parameters. Those parameters are, first one is phi, next one is P, next one is Z, and next one is A. So these are the parameters, and few more parameters is also there. I will discuss here. So here phi be the flux, P be the number of poles, Z be the total number of conductors in the armature, and these jet conductors, all the jet conductors are not connected in series. So they are divided into groups, and then let A be the number of parallel paths into which these conductors are grouped. So whenever the conductors are divided into groups, so these groups are consists of number of parallel paths, that is A. So each parallel path will have Z by A conductors in series. Z is the total number of conductors and A is the number of parallel paths. Okay, next. So here few more parameters is there, that is let N, there is a capital N, this is the speed of rotation in revolutions per minute. So let N be the speed of rotation in revolutions per minute. Okay, so here we consider one conductor on the periphery of the armature. So in the previous class, I taught you about working principle of DC generator. In that working principle, I took that two poles, that is north and south pole. So in between north and south pole, we are putting the conductor. So same here we consider one conductor on the periphery of the armature. So if the conductor makes one complete revolution, so it cuts P5 Webers. So in the previous class I taught you about, so whenever the conductor starts rotating, in the anti-clockwise direction, so the conductor moves parallel to the flux lines. Okay, moves parallel to the flux lines. So at that time there is no cutting of flux. That means there is no induced EMF in the system. So at the same time here also I am taking that as this conductor makes one complete revolution. So that means total complete revolution, that is for one cycle, that is 0 to 360 degrees. 0 to 360. So I already said that in the previous class, theta is equal to 0, theta is equal to 90, theta is equal to 180, theta is equal to 270, theta is equal to 360. So like this, if the conductor makes one complete revolution, means from theta is equal to 0 degrees to theta is equal to 360 degrees. So whenever the conductor makes one complete revolution, it cuts P5 webers. Here P is the number of poles and phi is the flux. Okay. So it cuts the P5 webers conductor. And next, as the speed is n rpm, so I already said that let n be the rotation speed of rotation. So here I am taking as the speed is n rpm, the time taken for one revolution is 60 by n seconds. 60 by n. That means if we take the rpm, that is the revolution per minute, we have n only. But I am taking here the time, that is the time taken for one revolution in seconds. That means it is converted into seconds, that is 60 by n. So per 1 minute we have 60 seconds. So depending upon that, the time taken for one revolution is 60 by n seconds. 60 by n seconds. At that time the speed is n rpm. At that time the speed is n rpm. That's why I am taking that the time taken for one revolution is 60 by n seconds. Okay. Next. So here the formula is, since the EMF induced in the conductor, is equal to rate of change of flux cut. Rate of change of flux, so I already said that flux is the phi. Here I am taking that rate of change of flux, that is d phi by dt. Rate of change, actually flux notation is phi. So here I am taking rate of change of flux cut, that is d phi by dt. So here from this condition, that is this statement, since the EMF induced in the conductor, that is E. So EMF induced in the conductor is indicated by the E letter. So that is equal to rate of change of flux cut, that is d phi by dt. Okay. So depending upon this, already we have the conductor cutting the flux, that is P phi. You know already the conductor cuts the flux for one revolution, for complete revolution. It cuts the flux is P phi. So I am putting that P phi in d phi place, divided by in dt place. That is, as the speed is n rpm, the time taken for one revolution is n by 60 seconds. So from that point I am taking that that is equal to 60 by n. 60 by n. That means P phi by n by 60. So P phi by n by 60, that is I am taking that E is equal to n P phi by 60 volts. That is the EMF induced in the conductor. E is equal to n into P phi by 60. N into P phi by 60. And next, since there are Z by A conductors, so I already said this point. So all the Z conductors are not connected in series, they are divided into groups. I said that point. So based on that one, so already I said that there are Z by A conductors in series. There is Z by A conductors in series, that is Z is the total number of conductors and A is the number of parallel paths. Okay. So here, since there are Z by A conductors in series in each parallel path, so the EMF induced is equal to EG, that is the generated EMF. Here EG means generated EMF. So that is equal to, already we have the EMF induced in the conductor, that is n into P phi by 60. So that into, here I am taking each parallel path for the conductors connected in series. Okay, that is Z by A. We already know that point. So from this one I am taking that EG is equal to 5P and Z by 60A. So note this equation, EG is equal to 5P and Z by 60A. This is the EMF equation of a DC generator. So note this equation, EG is equal to 5P and Z by 60A. Here pi is equal to, so pi is the flux, P is the number of poles, N is the speed in RPM and Z is the total number of conductors. and 60 is the time, and A is the parallel paths, number of parallel paths. So this is the generator EMF equation, that is Eg is equal to 5P and Z by 60A. Okay, this is the EMF induced in the DC generator. And next concept is, so here few more points is also there. Actually, the armature conductors are generally connected in two different ways. So actually we have the armature winding. So this armature winding are generally connected in two different ways. So those are lap winding and wave winding. So I will discuss this lap and wave winding in the coming topic. After this topic we have this one. So at that topic I will discuss this types of windings. Okay, so here the armature conductors are generally connected in two different ways. So those ways are lap winding and wave winding. So here for lap wound armatures, so if I am take that lap winding of the armature, so here the number of parallel paths is equal to number of poles. So please note these 2 points also. So for lap wound armatures, the number of parallel paths is equal to the number of poles for lap winding. That is, here the number of parallel paths is represented by A letter, that is A, that is equal to number of poles is P. So here for lap winding, the number of parallel paths A is equal to number of poles P. So similarly, in wave wound machines, the number of parallel paths is always equal to 2. In wave wound machines, the number of parallel paths A is equal to 2. These 2 points are very, very important for in the problem solving, in the problems. Okay, in the problems, these 2 points and that EMF equation is very, very important to solve the problems. Okay, so note those 3 points. The first one is the EMF equation of a DC generator is Eg is equal to 5PNZ by 60A. Okay, next for lap wound armatures, the number of parallel paths is equal to number of poles, that is A is equal to P. So for lap winding, A is equal to P. So for wave winding, A is equal to 2. Okay, so this is EMF induced in a DC generator or EMF equation of a DC generator concept. And next I am going to next topic, that is armature winding and its types. Armature winding and its types. So firstly we will look into armature winding. So here, so already you know that, so we have seen that there are number of armature conductors which are connected in specific manner as per the requirement. So we have seen that there are number of armature conductors which are connected in specific manner. So you already seen in the constructional details of DC machine. So here we have the armature conductors. Okay, there is nothing but armature winding. So here we have seen that there are number of armature conductors which are connected in specific manner as per the requirement. Okay, so which is called armature winding. So once again I am repeating the definition of armature winding. So there are number of armature conductors which are connected in specific manner as per the requirement. Which are connected in specific manner as per the requirement. So which is called the armature winding. Which is called the armature winding. So here this is the armature winding diagram. So here we have this is the armature conductor's position. So if you observe this diagram, we have stator or field. Here we have stator, and here we have armature conductors, and these are the poles, 2 poles, north and south poles. North and south poles we have, and next we have one commutator. So this one is commutator, and these 2 cement color one is brushes, brush 1 and brush 2, and this is the external load. So this one is the external load or battery. Okay, so this is the commutator, this yellow one, and these red and white one, these 2 are poles, and this one is armature conductor, and this one is stator or field connections. Armature and field connections. So this is the armature winding connection diagram, and next we will go into types of armature winding. So already I said that in the EMF equation. So the armature winding consists of 2 types, that is lap winding and wave winding. So here also I am taking that according to the way of connecting the conductors. According to the way of connecting the conductors, armature winding has basically two types. So according to the way of connecting the conductors, armature winding has basically two types, namely lap winding, second one is wave winding. These two. Okay, these are the two types of armature winding we have. So firstly we will take a lap winding. So this is the lap winding. So this is the lap winding. Here we have lap winding connection. So what is meant by lap winding? So here, so in this case, if connection is started from conductor 1 in slot 1, then connections overlap each other as winding proceeds. So till starting point reached again. So that is the lap winding. So if you observe the diagram, so I will show the diagram. So if you observe this, so what is the lap winding? So in this case, if connection is started from conductor 1. So this is conductor 1. So here the connection is starting. Okay, this is the connection. So in this case, if connection is started from conductor in slot 1. Okay, this is the conductor in slot 1. So then connections overlap each other. So here the connections are overlap. So this is the overlap conditions. So this one, 1, 3, 4, 5, 6, 2, 4, 6. These are the overlapping each other as winding proceeds. As the winding proceeds till starting point is reached again. This is the starting point and this is the starting point. Okay, this is the starting and this is the starting. So this one is called as a lap winding. So what is meant by lap winding? So if connection is started from conductor in slot 1, then connections overlap each other as winding proceeds. So till starting point is reached again. Till starting point is reached again. So this is starting point and this one is also starting point. Okay. So in between the winding is proceeding by overlapping each other, by overlapping each connection or each conductor. Okay. So this is lap winding. And here a few more points is also there. So these windings are used in machines designed for low voltage and high currents. So these are used in machines designed for low voltage and high current. So only these windings are used for low voltage and high current machines only. Low current and high current machines only. So here armatures are constructed with large wire. So here the armatures are constructed with large wire because of high current. Because of high current. So why? Because these armature windings, so this type of armature, that is lap winding, is designed for low voltage and high currents. So that's why armatures are constructed with large wire because of high currents. Okay. Next. So here the windings of a lap wound armature are connected in parallel. So the windings of lap wound armature are connected in parallel. So if you see this diagram, so here this is connected in parallel. So these wires are connected in parallel. This is the parallel connection. Okay. So this permits. So the winding of lap wound armature are connected in parallel. So this permits the current capacity of each winding. So this permits the current capacity of each winding to be added and provides a higher operating current. So actually the windings of a lap wound armature are connected in parallel. You already know that. So this permits the current capacity of each winding. So this permits the current capacity of each winding to be added and provides a high operating current. Example, these are used in the starter motors. These lap wounding machines are used in the starter motor of almost all automobiles. Using this lap winding. So here already I said that in the EMF equation, number of parallel paths is equal to number of poles. Here the number of parallel paths is indicated with A letter and number of poles is indicated with letter P. So that is here A is equal to P. This is for armature and lap winding. And next armature wave winding. So this is one of the type of armature winding. So if you see this diagram, so in this one, so in this type of connection, winding always travels. Winding always travels ahead. Winding always travels ahead, avoiding overlapping. Avoiding overlapping. Avoiding overlapping. So here, in this type of connection, winding always travels ahead, avoiding overlapping. So it travels like a progressive wave. So here, this travels like a progressive wave. So if you see this one, so it is a travel like a progressive wave. So in this way, it travels. So it is looks like a progressive wave. Okay, it is look like a progressive wave. So next, hence called wave winding. So in this type of connection, winding always travels ahead, avoiding overlapping. So in the previous case, it is overlapping, but here in this case, it is not overlapping. Okay, it is avoiding overlapping. So it travels like a progressive wave. Hence called it is a wave winding. Hence it is called as a wave winding. And next, so both coils starting from slot 1 and slot 2 are progressing in wave fashion. So both coils starting from slot 1 and slot 2. Both coils are slot 1 and slot 2. So here this is one coil, it starts from the slots from 1 2, and another one is 3 4, and next one is 5 6, next one is 7 8. So in this way it travels. Okay, so both coils starting from slot 1 and slot 2 are progressing in wave fashion. So this one. So 1 2 3 4 5 6 7 8. So like this it is traveling. So these are used in machines designed for high voltage and low current. High voltage and low current. Okay. So in the previous case, what happened? The lap winding is designed for low voltage and high current. But this type of wave winding is designed for high voltage and low current. High voltage and low current. High voltage and low current. So these windings are connected in series. So these windings are connected in series. Okay. So in the previous case, those connections are in parallel. Okay. In the previous lap winding, the windings are connected in parallel. So here in this case, the wave windings are connected in series. So here, when the windings are connected in series, the voltage of each winding adds. So when the windings are connected in series, the voltage of each winding adds, but the current capacity remains the same. Here the voltage is adding, current is same. Okay, so these are used in the small generators. Okay, next here in this case, so actually in the lap connection, number of parallel paths is equal to number of poles, but here in this case number of parallel paths is always equal to 2. Okay, so this is the types of armature winding, that is lap and wave winding. And next concept is comparison of lap and wave winding. So this is important one. So comparison of lap and wave winding. Maybe it will be asked for 2 mark or 5 mark questions in the external examinations. So I already said that in lap winding, the finishing end of the one coil is connected to the starting end of the adjacent coil. So in lap winding, the finishing end of the one coil. So the finishing end of the one coil is connected to the starting end of the adjacent coil. So this is the finishing end of one coil and this is the starting end of one coil. So starting end of the adjacent coil, this is called as lap winding. So in the wave winding, the wave winding is designed like a wave. So the wave winding is designed like a wave. So I already said that. So in the wave winding, it avoiding overlapping. So it's avoiding overlapping. So and it travels like a progressive wave. Hence it is called a wave winding. I already said that. Same point here also. The wave winding is designed like a wave. Okay. Next, second difference is EMF generation is low in the lap winding because number of conductors in parallel paths is less. So EMF generation is low because number of conductors in parallel paths is less. Number of conductors in parallel path is less. And compared to wave winding, so in the wave winding, EMF generation is more because number of conductors in parallel path is more. Number of conductors in parallel path is more. Okay. And next third one is in the lap winding, number of parallel paths is equal to number of poles. Number of parallel paths is equal to number of poles. So in the wave winding, number of parallel paths is equal to 2. Number of parallel paths is equal to 2. And fourth one is it is suitable for low voltage and high current applications. So I already said that in the lap and wave winding explanation. So lap winding is suitable for low voltage and high current applications. Similarly, wave winding, so it is suitable for high voltage and low current applications. High voltage and low current applications. Okay, next one more point is also there, that is actually the lap winding is used for generators of capacity more than 500 amperes. More than 500 amperes. So note this point. So normally the lap winding used for generators of capacity more than 500 amperes. So in the wave winding, these preferred for generators of capacity less than 500 amperes. So why? Because wave winding is used for low current applications. That's why the wave winding is designed for generators of capacity less than 500 amperes, and the lap winding is used for high current applications. That's why this lap winding is used for more than 500 amperes. More than 500 amperes generators. Okay. So this is the comparison of lap and wave winding. Thank you.